Thank you for tuning in to the Pison team. This is the hand gesture classification project where we use video labeling off of video-based signals. Team members Colin Davis and Jamie Gagnon. Our technical directors for this project were Xiaofeng Tan, Director of Algorithms for Pison, Matthew Fleury, Machine Learning Team Lead, and our Substitute Technical Director, Henry Valk. This project was completed by computer engineering student Colin Davis and computer engineering student Jamie Gagnon. Now for a brief company overview. Pison Technology was founded in 2016. They began dealing with issues within the ALS community. They set out to help those who could no longer use their day-to-day technologies due to their condition. This is a human performance company that intends to optimize the cognitive and physiological capabilities through gesture control. Our anticipated best outcome has been changed since the beginning of the year. Initially, we were set out to create a fully operational machine learning pipeline that is fully automatic. However, the scope of this R&D project has been shifted, and we then reevaluated and discussed that we should create a semi-automated data labeling pipeline that can define different gestures that it reads. Data collection is the most important and time-consuming task, which is why having an automatic machine learning pipeline set up would put Pison's hand gesture project on a solid path to developing a fully functional commercial model. However, we decided to work with another company called Roboflow, which we will get to later on, and this company helps us get a better idea of the data that we are consuming. Our project's motivation. As discussed earlier in this presentation, Pison is a human performance company that intends to optimize the cognitive and physiological capabilities through gesture control. And in order to do that, you can see a prototype on the right of one of the Pison devices that would go on your wrist. And this is intended to be a commercially usable portable device that uses electrodes to sense the EMG signals that go through your wrist. Now, using a machine learning model, we can determine the gesture classification. You can see some examples of gestures in the bottom right. The uses for this classification are endless. We can use it for robotics and drone implications, flying drones, controlling robots. It can be used in the military and DoD, and has geolocation use cases, as well as a compatibility with AR and VR technologies.
We did in fact reach our anticipated best outcome for this project. It was adjusted for the project's original best outcome. We met the specifications of the new ABO using the following algorithms to detect the onset/offsets of each person's hand gesture data through the sessions given. Some were more efficient than others in the detection of these onsets and offsets in both pronated and semi-pronated hand gesture sessions. During this project, we have done a wide variety of tasks in aid in its completion. We started last semester with merging the datasets and syncing the timestamps, as well as using KWL and DTW algorithms to evaluate the data. After we got back from winter break, we started working on Roboflow annotations to help speed up the process. Then, as soon as the semester started to kick in, we started working on benchmarking, biosignals, as well as visualization of the data. Finally, all this would lead into the optimization of all the scripts. The economic impact this product presents is that it would eventually create the first fully automated data labeling algorithm to aid Pison in future applications. Such a product would be very marketable to many of Pison's investors, as well as leave a solid foundation for future technologies to come. Here is the adjusted block diagram that originally in the project proposal, Roboflow was not in the picture. However, as you can see, they are very much integrated into the structure of the pipeline. You can see in the block diagram to the left that Roboflow machine learning pipeline makes API calls, and in turn returns the gesture it has labeled. In the original diagram, we have the Pison device pushing BLE data to the Pison server via an Android phone, thus using Azure to store the data into the cloud, then evaluating the data via a notebook server on Google Cloud Platform. On the right, we have a more in-depth look at the pipeline and how it merges data, as well as labeling the data. This concludes our introductory. Starting our technical accomplishments will be Colin.
Hello everyone, my name is Colin Davis, and these are my personal technical accomplishments for the Pison project. For this project, my first technical accomplishment was working with the DTW algorithm, or also known as dynamic time warping. The DTW algorithm works by matching two different timed series together and finding the similarity between them. For this project specifically, we use two approaches, the independent DTWI and the dependent DTWD approaches. For DTWI, we calculate the DTW distance for each feature independently and average them, while DTWD, we calculate the DTW distance between all features at once. We randomly select 15 training samples for each gesture, and then calculate the DTW distance between the sample and each of the training samples for the given gesture, and take the averages over all the distances. Now, we noticed after doing this that there was definitely a thresholding issue and a dataset issue. We didn't have enough datasets that had the confidence level needed in order to create solid thresholding data, and DTW runs off of good thresholds. So the fact that we did not have enough data in order to create a solid threshold would also make the DTW algorithm less effective, and we'll talk about that later on as well. Biosignals and Hodge's onsets detection was another algorithm that we were tasked by our TDs to implement for this project. This algorithm has been used in-house by Pison on multiple occasions, so we only had to rearrange the script to meet what we needed in order to get it working. This algorithm will act similarly to the other ones, as its main goal is to calculate the onsets and offsets, but using certain thresholds and sampling rates. The sampling rate for this project is 600 Hz. It is a signal-based onset detection that uses the Tager-Kaiser energy threshold and based on impulses that can detect onsets and offsets. The runtime for this is extremely fast, and there's a few false detections, but overall it was very effective. Benchmarking and optimization was another big aspect of this project. I used a script that allows the ability to understand how accurate each algorithm is compared to the ground truth dataset, which Jamie will talk about later on, as well as figure out what tweaking needs to be done to make the algorithms more accurate and more effective. For KWL, we noticed it had a good overall detection, but was very sensitive on the onset side, causing prolonged detections. For DTW, we had bad original threshold data, which I discussed earlier, and needs to be reevaluated, and possibly more data needs to be pushed through the pipeline in order for this to be an accurate algorithm to use. The Biosignals and Hodge's onset had great overall detection and is fairly accurate, but could use some improvement on the offset detection. The optimization aspect of this project was repurposing previous optimization scripts for the KWL and Biosignals in order to get better values for these functions and algorithms to be run in the future. The only prevalent issue is that the failure ratio is higher than the initial test after the optimization. A few changes were made to some of the functions while testing the onsets and offsets. The mistakes outside of the true activation region were being weighed more heavily than the mistakes inside of the activation region, which means early onsets and late offsets were penalized more than late onsets and early onsets, since the former leads to more mislabeled resting samples, while the latter leads to mislabeled activations. Also, the penalty was increased for having an incorrect number of activations. Therefore, this value, which was initially plus 30, has been changed to plus 200 and possibly plus 400. And these tests were run multiple times to figure out which new values could be run and then test against the benchmarking set to see which was better. Overall, it still seems that Biosignals is more accurate overall and has the best bounds. And the key takeaway from this is that we can, for right now, as of now, we should be using signal-based onset detection instead of video labeling onset detection until we have a better video labeling onset data or algorithm to use in the future.
Hi, my name is Jamie Gagnon, and here are my technical accomplishments for the hand gesture classification project. In order to fluidly evaluate the data in the pipeline, the data needed to be merged. Earlier in the slides, we showed you two block diagrams. The block diagram that was on the right had an initial step of merging the data. As you can see, this graph shows the timestamps have no offset difference, and they are fully synchronized. KWL was originally an algorithm that one of our TDs, Xiaofeng Tang, created. Kurtosis was used to help aid in the detection of onsets and offsets. This was considering the fact that the algorithm was used to detect the kurtosis of the waveforms. Here we have an example of the manual onset detection interface we used. This was to help us better define where the actual onsets and offsets were. There were a lot of sessions, and out of the collections of data that we were using were no good. To define the true onsets/offsets, this had to be done. After we had implemented various algorithms to aid in the detection of onsets/offsets, we had to see how efficient each algorithm was. This in turn was done by using matplotlib to cycle through each gesture in the dataset, as well as using synchronized graphing of each algorithm, displaying them on each graph for each gesture to see the difference. This was a technical accomplishment of both me and Colin, since we both worked on Roboflow annotations as well as other tasks involving Roboflow. Roboflow was used to speed up the process, as said before. As you can see, the results of the precision and accuracy of the model are very promising on the leftmost image. The gesture labeling statistics of the model is the leftmost image. And the other reading is from the transition data of the model, and you could tell the difference between a transition and a full hand extension hold or whatever gesture. But on the right, it is a full extension hold, and the model can tell the difference between transition and that particular gesture. Summarizing, we have completed a semi-automated pipeline and trained it to realize true onsets/offsets. This project was a step in the right direction for Pison for the years to come. The project will be continued by Pison technology and eventually leading to a fully automated data labeling algorithm. I'd like to thank Matthew Fleury as well as Xiaofeng Tan for being our technical directors through the process of this project, as well as a special acknowledgement of Henry Volk. He really filled in the void of a technical director, even though he really didn't have to. Also, I'd like to thank our consulting technical director, Brendan Smurbeck, as well as the ELECOMP director, Dr. Haris Sunak. This concludes our presentation, and thank you for watching.